Okay, guys, welcome back. We're in 3B and we're going to look at induction for divisibility results or just proof of mathematical induction involving some kind of divisibility. Now, here's our question. There's a few kind of key differences when we're doing the divisibility proofs. One of them is you're going to notice there's no right-hand side to this equation. It's also not in any form of summation. So, like I said, those two things are a little bit different. So let's just write this out. I have n cubed minus n is divisible by 3. Now, there is another way to write this line out because it's quite long and mathematicians like having shorthand ways of explaining the same idea. The way we do this is with a vertical bar. So we would say 3, we put our nice little vertical bar or a vertical line here, n cubed minus n. Then I'd put my conditions, n is greater than 1, n is less than 1, or in this case, n is natural numbers, where n is an element of natural numbers. Again, natural numbers don't include 0, and they only include positive numbers. So 1, 2, 3, 4, 5. You could think of natural numbers as being positive integers, same kind of idea. So whole number values. So with any type of divisibility question, we always have kind of the same idea. What I'm trying to prove, or I guess kind of the formula I'm working with, is the idea that n cubed minus n is going to be equal to 3m, where m is also going to be a natural number. The reason n's a natural number is if I have only positive values and I'm cubing one of them and I'm subtracting it, it's the same number. It's always going to give a positive answer. So I can use natural numbers. If it's possible to get negatives, then I could just put where m is some integer or some form of whole number. So this is kind of what I'm trying to prove is something like this, where n cubed minus n is divisible by 3. We can kind of think of it this way. In terms of breaking this up into our steps, just bear in mind, we don't need to show this working out. We can simply start here at my test step. So I want to test. So I'm going to test if n's a natural number. Like I said, it doesn't include 0. So I'm going to start at the number 1. So test n equals 1. If I do n equals 1, I get 1 cubed minus 1. That's going to equal 0. Now, technically, 0 is divisible by 3. If I have 0 divided by 3, I get 0. So I get a perfectly acceptable number. So I can't actually get 0. Because I can get 0, I should really change, because m could be 0. 0 is not a natural number. I'm just going to change this to being... I'm just going to change m to being integers. So it's just going to be whole numbers. It's going to include 0 in that case. It also will include negatives, but if we don't get a negative, we're fine. It's still part of that bubble of integers. So I get 0. This is technically going to be true. However, if you're unsure, we could always test the next value along. So if I did do n equals 2, that would be 2 cubed minus 2, which would equal 6. Now we know 6 is definitely divisible by 3, because I could write this as being 3 multiplied by 2. So 2 whole numbers, 3 times a whole number means it must be divisible by 3. So therefore, I can say it's also true based on that. So I do n equals 1 and I get 0. That is actually fine and would be acceptable. If I do n equals 2 and I get 6, obviously that also is going to work for our proof. So both these values are true in this case. I don't actually need to show both, but I just want to kind of clarify. If you see 0 and you're not sure, you can always do the next one along. And you'd still get 4 marks. Step 2 is going to be to assume. So I'm going to assume that n equals k. And at this point here, this is where this idea is going to come in a little bit more handy. So if n equals k, that means I have k cubed minus k. I'm assuming this is going to be divisible by 3. So I can let this be 3m, where m is an integer. Now I'm going to do my prove step, or I could write RTP, required to prove, for n equals k plus 1. In this case, this is going to be k plus 1 cubed minus k plus 1, and that's going to equal 3. In this case, it's going to be a different number, so let's just choose, I can't use n, let's just choose p, where again, p is going to be some whole number value or an integer. So with my proof by divisibility, one of the things that are a little bit different is I can only look at the left-hand side for a proof like this. So I'm going to try to show my left-hand side is equal to 3 times some whole number. In this case, I'm calling that whole number p. So if I look at my left-hand side and I let that equal k plus 1 cubed minus k plus 1. So if I expand out my cubic here, some of you might remember from binomial expansion and methods, this cubic here relates to the third row of Pascal's triangle, which looks like 1, 3, 3, 1. That means it's going to be a coefficient of 1, k to the power of 3 plus 3k squared times 1 plus 3k times 1, which is just going to be 3k plus 1. And then my bit on the end is going to be minus k minus 1. If you're a little unsure about this expansion of my power of 3, you could just write out k plus 1, k plus 1, k plus 1, do a series of kind of FOIL methods, and you should get to the same line. So once you get to here, instead of collecting like terms like I normally do, whenever I'm doing a proof by divisibility, what I'm always trying to look for is how I can get an expression like this in my left-hand side. So it's still a little bit similar to our normal proof by induction methods. The reason why I want this is I want to try to work this 3m into my left-hand side solution. That part is key to actually solving a question like this. So I want to, instead of collecting like terms, I want to first look at my line of mathematical working and see if I can find a k cubed minus k anywhere inside this. Sometimes it can be a little bit hard to find, and then you might want to collect like terms and try to do some of our algebra skills to find it. This also can lead to some quite creative thinking for how we can get this left-hand side here into my left-hand side when I have my k plus 1 term, because it's a little less straightforward than our normal proof by inductions. If I have a look here at my numbers, though, we can see I have a k cubed minus k here like so. So now all I'm going to do is I'm just going to rearrange my equation to get k cubed minus k next to each other. If I do that, that's going to equal k cubed minus k plus 3k squared plus 3k, and then 1 minus 1 is just going to become 0. If I now substitute 3m in place of this, I'm going to wind up with this being equal to 3m plus 3k squared plus 3k. Now, hopefully you guys can see 3 is a common factor. I'm going to get the result I'm looking for. So I take my 3 out the front. I have 3. It's going to be times m plus k squared plus k. Now, remember, these m's and these k's are all going to give me some whole number value. If m's a whole number plus another whole number squared plus another whole number, I'm going to get some integer as my solution. Because I'm going to get an integer as my solution, I can say that m plus k squared plus k is going to be equal to, now I can pick any letter. I'm going to pick p simply because I used p here. So if I put p in here, this is going to equal 3p. I don't necessarily need to do this explanation part either, because I've already established that p is some whole number, and I know that this is just going to give some whole number. You know this is going to give some whole number. You're communicating that answer by simply writing down my whole number here. So now you can see this equals 3p, which equals my right-hand side. So that is my proof with divisibility. The only step I'm missing is my explanation part. Therefore, showing true for n equals 1, assume true for n equals k, and prove true for n equals k plus 1 by mathematical induction. So this is my proof using mathematical induction for divisibility. The key differences here is I have no right-hand side of my equation. So the way I want to establish this is whatever I'm dividing by, if I'm dividing by 3, for example, it's going to be 3 multiplied by some whole number. If I was dividing by 4, it would be 4 multiplied by some whole number. The steps are still the same. So test for n equals 1. If that is true, and then assume for n equals k. When I do this step, I need to include a right-hand side that matches whatever I'm dividing by. So if I'm dividing by 3, it should equal 3 times m, where m is going to be some integer. For the required to prove part, that part all stays exactly the same. The only difference is when I'm trying to assess my left-hand side, instead of just collecting like terms and trying to simplify and factorize as much as possible, instead I'm trying to work my equation to get the left-hand side from my assume step, which in this case was k cubed minus k. Once I've kind of found that within my left-hand side, and will always be part of the left-hand side, always, so there's always a way to get it, then I substitute in my 3m in this case, take out 3 as a common factor, and then I can let this kind of brackety bit just be equal to some whole number, and I can get my final solution.